Hello everyone, thank you for joining with us. We are excited to present our project titled Curtain Grouting Pattern Incorporating SPT N-value and Lugeon values. This project focuses on developing a scientifically driven, site-specific grouting design to enhance dam foundation stability and reduce seepage effectively. We are group number 8. Together, we have worked on this detailed study integrating field investigation, data analysis, and design methodologies to create an analytical data-driven grouting method. Let's start with some background on why grouting plays such a vital role in dam engineering. In essence, grouting is used to seal permeable rock fractures under dams. This reduces the seepage of water through the foundation, which is critical to maintain reservoir water level and overall dam safety. When grout is injected into these fractures, it hardens and significantly lowers the hydraulic conductivity of the rock mass beneath the dam. In Sri Lanka and many other places, dams often face seepage issues due to natural variability in geology and rock fracturing. If untreated, seepage can cause increased uplift pressure beneath the dam, leading to instability and even potential failure. A grout curtain acts like an impermeable barrier beneath the dam, reducing water loss and lowering uplift forces. However, the curtain must be carefully designed to prevent excessive hydraulic gradient that could cause erosion along partially sealed fractures. Traditionally, grouting designs have been empirical, relying heavily on experience and standard layouts that do not always adapt well to site-specific conditions. This is why adopting a more data-driven approach, one that fully utilizes site investigation results, is so important for improving dam safety and construction efficiency. Our main aim was to develop a data-driven, site-specific curtain grouting methodology for dam foundations. This means creating a grouting design approach that is not only efficient but can adapt to the varying subsurface conditions we encounter at different sites. We also wanted to overcome the usual limitations of conventional grouting methods, which often rely on standard patterns without fully using site data. To achieve this, we set 4 clear objectives. First, to thoroughly assess and understand the subsurface conditions using the standard penetration test results and Lugeon permeability tests. Second, to develop grouting methods tailored to different geological conditions. Third, to design an optimized grouting pattern that specifies the spacing between grout holes, curtain thickness, and how far grout should spread to effectively seal fractures. And finally, to establish a comprehensive grouting procedure, including guidelines on grout mix adjustments, when to stop grouting, and criteria for redrilling if needed. Together, these aim and objectives guide our project to provide a scientific, efficient grouting design adapted to local conditions. For the literature review, we referred to several important sources to build a strong foundation of knowledge for our project. We studied seminal work such as Warner's Practical Hand of Grouting, detailed research papers on grout curtain design, and case studies on dam foundation grouting projects. These resources provided both theoretical insights and practical methodologies. Importantly, we used the numerical formulas and calculation methods from these references to guide our own design process. They helped us understand how to estimate grout thickness, spacing, and pressure parameters scientifically, rather than relying solely on empirical or traditional methods. Now, I'll briefly outline our project methodology, which is structured into 4 main parts. First, we gathered comprehensive site investigation data and crucial data on soil and rock conditions. Next, we developed a detailed subsurface model by integrating and visualizing this field data to identify weak zones needed to be treated. From there, we selected the key parameters for the curtain grouting, including grout mix, curtain thickness, hole spacing, and injection pressure tailored to the site conditions. Finally, we designed the grouting pattern itself based on our calculations to ensure effective coverage and foundation stability.
Now moving on the site investigation, this was a critical step because it gave us detailed information we need about the subsurface conditions. We used 3 main types of data. First, the standard penetration test or SPT, which involves driving a sample into a soil and counting the number of blows needed. This gives us an N-value that tells us about soil density and strength, which is key understanding how well the foundation can support the dam. Next, water pressure test, also known as a Packer or Lugeon test. In the rock boreholes, here isolate specific intervals of the rock and inject water under controlled pressure to measure how much water is absorbed. This test reveals the rock's permeability and how fractured it is, crucial for assessing potential seepage paths. Finally, we have done the core sampling through drilling. For these samples, we got the rock quality designation. This indicates how intact the rock mass is. Higher RQD means fewer fractures and better rock quality, which guide us in deciding where and how extensively to grout. Together, these tests gave us a comprehensive picture of both the soil and rock conditions, which allowed us to tailor the grouting strength effectively. Let's talk about how we built the subsurface model, which was a key part of turning all the field data into something usable for our grouting design. First, we gathered all the borehole data. This includes the SPT N-values and the Lugeon water pressure test results. We compiled this raw information into Excel and carefully cleaned it up, fill in any missing intervals to ensure we had consistent data for analysis. Next, we imported the borehole coordinates and these attribute tables into QGIS. This allowed us to place every test points accurately on a map using QGIS 3D visualization tools. We displayed the borehole in 3 dimensions and color-coded each point according to its test intervals. This visual approach helped us to quickly spot patterns and variations partially, such as zones where soil was weaker or the rock was more permeable. To get a clearer vertical picture of permeability variations, we used starter software to create geological cross-sections based on the Lugeon test data and RQD data. These cross-sections shows us how permeability changes with depth, which is crucial for understanding water flow and seepage potential. Then integrated these cross-sections right below the 3D visualization in QGIS, giving us both horizontal and vertical references in one view. This combined view made it easier to interpret the overall subsurface conditions. Finally, by comparing variations in SPT and Lugeon value across these boreholes, we identify weaker zones, those areas with low soil strength or high permeability, which becomes our primary targets for the curtain grouting design. This slide presents the key equations and relationships used in the design phase of the curtain grouting process. It includes the formulas applied to determine the thickness of the grout curtain, and the depth of individual grouting intervals. Additionally, it illustrates the equations and graphs used to estimate the appropriate grouting pressure, ensuring the prevention of hydraulic jagging and the reductions of uplift pressure on the dam foundation. Using these numerical methods, a curtain grouting pattern was designed for the rainwater harvesting project in Vadamarachchi lagoon. This slide explains the termination and refusal criteria derived for the design calculations. It illustrates how cement to water ratios are selected based on grouting intake and identifying the critical time limits for terminating the grouting process. The chart shows here represent for a 50-meter sections along the dam axis. When initiating the complete design, similar calculations must be carried out for the remaining length of the dam to finalize the overall grouting plan. Here is the final grouting pattern developed for the rainwater harvesting project in Vadamarachchi lagoon. It illustrates the required number of arrangement of boreholes to be drilled for grouting, the expected spreading distance of grout flow, and the grouting intervals that must be considered during operations in this region.
In this part, I am going to explain the financial analysis part of our design project. This slide shows the cost calculation section of our study. In the traditional method, major water leakage occurred due to inefficient grouting. However, based on our improved design, the leakage is reduced efficiently. Although this design requires additional grouting cost, it helps to save a large amount of water that can be used for agricultural purposes. The financial analysis shows the additional cost can be recovered through the value of the saved water. The payback period is 5 years, meaning the investment can be recovered within 5 years. Moreover, the NPV and BCR values are positive, that indicate project is economically viable and profitable. As benefits, our new design cost more at first but save money later. It reduces water leakage, improves dam safety, and remains effectively for a long time. It also protects the environment and supports farming by saving water. Finally, we can conclude that project is more viable and profitable when considering all aspects like financial, technical, environmental, and social. Okay, these are the references. Thank you.